Okay, we've talked a bit about biodiversity, and we've talked about how important it is and how some biomes have more of it than others. For instance, we've said, oh, well, a rainforest biome that has very high biodiversity, and a desert biome has very low biodiversity. But how exactly do we put numbers on that? That's what we want to look at today. Okay, so if I get my slide to advance. There we go. The two main factors we want to consider when we're measuring biodiversity are richness and evenness. So richness is a pretty easy concept to get your head around. It's just basically how many different species happen to be present in a given area. So if I'm studying a particular forest, I might map out an acre of it and say, okay, how many species do I find here? That's my richness. Now, it doesn't matter how many of any individual organism there is. There could be like one butterfly or 10,000 of the same butterflies, but that counts as one species, okay? But just how many species are there, that's richness. Evenness has to do with, of all the organisms that are present, how dominant is a particular species here. So what we find is that if the species tend to be all fairly evenly represented out of the total population, we say we have high evenness. If certain species, like one or two species, are predominant and the other ones are in much more minor presence, then we say we have less evenness and therefore less biodiversity. So you can see it's a little harder idea to get your head around, but don't worry, we've got a way of handling it here that we're going to talk about. So let's just take a look at a couple examples here. So if I look at the one over here, I see I have greater richness, and that's because I have a total of 1, 2, 3 species. Now, it doesn't matter how many of the red butterfly I have, the number of species counts as 1, 2, 3. Over here, I just have 2 species. So here, I have greater richness. But if you look over here, this butterfly dominates. There's 6 of this butterfly and just 1 of the dragonfly and 1 of the beetle. But if I come over here, I have better evenness because I have 4 butterflies and 4 ants, and so the distribution of the population is more even. That's the difference between the two. I think if you look at this slide, hopefully you get the idea. Here's another one here. So if I look at community 1 and community 2, they might not look that different to you, but if we look, what we have basically in both cases, we have 4 species of tree. But in community 1, those 4 species, if you look, I have 4 of each of them. So I have 4 of this one, I have 4 of this one, I have 4 of this one, and so on. So each tree species accounts for 25% of the population that I have here. Now I have the same 4 species here, so I have the same amount of richness. However, if I notice, this one here seems to dominate. In fact, 70% of the trees come from this one species. 12 come from this. 12 come from this, and only 6% come from this one here. So there's a lot less richness here. So we would say that this community here, although it has the same number of species, is less biodiverse than this one here. Now, how do we go about putting a number on it? Ooh, look at this. This looks like fun, doesn't it? Actually, it is pretty cool. So we're going to use a thing called the Shannon Wiener Diversity Index. And basically what you do is you use the relative proportion. So just think of it as what percent, as a decimal percentage, you have of each species in terms of the total count of organisms present. And what's nice about this is it allows us to account, as we'll see, for both richness and evenness. And so the higher the value you get, the more biodiverse an environment is. So it gives us a way of putting a number. We say, here's the number that we have for the Amazon rainforest, and here's the number we have for the Sahara Desert. So just a couple of terms here. First of all, H stands for biodiversity. I don't know why they used H, to be honest. It is equal to the negative sum of the following. P is the percentage of a particular species. So what percentage do the individuals of this species make up of the total population of organisms found? So what decimal percentage times the natural log of that same percentage for the same organism. So let's just try working through this and see what we get here. Okay, so let's go and look at this one here. So in this case, I have 25%, 25%, 25%, and 25%. So the percentage of this would be 0.25 times the natural log of 0.25. So that's what I would do here. And that gives me negative 0.35. So that's what I get for each of these, right? So the sum, since they all are the same, 0.25, When I sum these up, I get this, which is negative 1.4. But remember, I'm taking the negative of it, just so I'm not dealing with negative numbers. I'm not confusing people by saying, is a bigger number more or less? So that's why we take the negative. So here we get for this particular ecosystem, we say, well, the biodiversity is 1.4. Okay. Let's look at the other one we had, the one that had, we said, same richness but less biodiversity because there was less evenness. So if we look at this one here, what I'm going to get is I'm going to have 0.6 times the natural log of 0.6 gives me negative 0.17. I'm going to have 0.12 times the natural log of 0.12 gives me negative 0.25. Now, interestingly, if I say 0.7 times the natural log of 0.7, I also get 0.25. And then I have 12% again, so I get this. So when I add all these up, what I get is negative 0.93. So when I take a negative of that, I get 0.93. So look, we said that this one was less diverse, and when we use the Shannon-Wiener index, what we get is the more diverse one got us a rating of 1.4, and the less diverse one got a rating of 0.93. Now, what if we had 5 species instead of 4? Let's face it, 4 is not very many. So if we have more species, what does that do to our number? Well, in this case, I didn't get another graphic, but let's just say what I had here was 5 species that were all evenly distributed, so that each accounted for 20%. I would have 0.2, that's 20%. All right. 0.2 times the natural log of 0.2 is negative 0.32. I would have that 5 times because there's 5 species. So when I sum up for all the different species, I would get this, and that gives me 1.6. So you see that it got higher because I had more species. So this Shannon-Wiener index takes into account both richness as well as evenness. So here we have the one that had 4 species was 1.4. When I added the next species, if I kept the evenness the same, I got 1.6. But let's be real here. I mean, if you were to go into an environment like we're looking at here, it's kind of hard to count all the species, right? There's a couple problems we have. One is there's a lot of them, so it gets hard to count. Now, if you're a trained botanist, for instance, or a I'm trying to think of the word for people who study insects, entomologists. Yeah, you have a better chance of this, but you know what? There can still be a lot of them to count. It might be kind of hard to do. Another thing is that the animal species, they tend to come in and go out. So coming up with an accurate way of counting biodiversity is a little bit tricky. If you define your methodology, you can still get numbers that allow you to make relative comparisons. But the reality is, in the actual real world, it's very difficult to measure biodiversity. So scientists have come up with a number of techniques. These are the main ones we have. We have what's called canopy fogging. It's as bad as it sounds. Quadrant sampling, transect sampling, and netting. It's as bad as it sounds. Let's just try this here, okay? So let's start with canopy fogging, okay? Literally what you do is you lay down a bunch of plastic sheets to catch your victims. You go up into the canopy of a tree. I'm not sure how this guy actually got there. It looks like he climbed up. He's got no mask on. And you basically spray insecticide death into the canopy and just basically kill everything. And then everything drops down onto here. Now, it may seem like this is a bad idea, but in reality, you can actually save more species if you develop an understanding of biodiversity than you kill by gassing them out of the trees. But basically, this is one way of getting a count of what's there and applying this this index, this Shannon-Wiener index. Another thing you can do is called quadrant sampling. So quadrant sampling is basically you define an area, often like a square meter area using like plastic pipes. And then sometimes you subdivide it. And you just basically try to use it to count what species are present in each portion of this. So you're going to take a square area that's fairly easy to move around, and you're just going to count the species that are inside. This is mostly used for plants, but I suppose with photography or video, you could probably do it for some of the mobile insect species as well. But again, you're just going to take this area and you're going to count all the species in it, and you're going to apply it to the Shannon-Wiener index. Now, sometimes instead of laying out an area, we can do what's called a transect. So a transect happens when we just lay out some sort of a line and we just go along the line and we're just going to count every single organism that comes into contact with this line. So I could lay it across the desert, I could lay it across a coral reef, and I'm just going to go along and record every single thing this line goes over. It's just a way of randomly choosing what species are going to be counted. And then finally, we have what's called netting. Netting is done often to catch flying organisms or swimming organisms. It's basically what it sounds like. You put a net out, things get caught in the net, and you count how many individuals of which species got caught in the net. And yeah, it kills a lot of them. But again, the feeling is it's worth it in order to study biodiversity, because by understanding biodiversity, we can protect biodiversity. So that's how we're going to measure it. And when we come to class, we're going to have an activity where we measure biodiversity of a parking lot in terms of the car species that are present.